Hello, I'm Anjali, and I'm a master's student in mathematical and theoretical physics here at Oxford. And I'm joined today by Professor Steve Simon, who is a condensed matter theorist. And I also took a couple of lectures with you earlier this year. And I'm very delighted to have you here.
Very happy to be here.
All right, to kick things off, is physics something you've always wanted to do?
Yeah, I think so. When I was very small, I became very enamored of math. And, my mom was moving out of our house. She's in her late 80s and going through the things in the attic. And she found a piece of paper that I wrote when I was 7 years old. And it said, "I like equations." Even that, they used to sort of, just to keep me occupied, when driving in the car and not screaming, my parents would ask me, what do you add to 7 to get 12 or something like that? And I would think, oh yes, 5. And that would keep me occupied for hours. And then I just sort of started to love math, and when I was in elementary school, I started, making up math and reading math books. I remember one in particular, I think it's still used. It's called Mathematics: A Human Endeavor. And I think I read it when I was, I don't know, in 5th grade or 6th grade or something. And it's not a hard book, but it has all sorts of aspects of mathematics in it. And I just absolutely fell in love with it and kept reading more and more. And then I was introduced to physics for the first time, I guess, in high school. I don't know, maybe my second year of high school or something. And I was like, okay, this is what I want to do with math. This is the interesting, this is what math is for.
Mm-hmm.
And I pretty much, I did think about other possible careers along the way, but I kept coming back to physics. This is what I really like, applying this lovely mathematics to something real in the world. And I was pretty sure that I was going to be a physicist thereafter. So that was how I got introduced to the subject. I guess I was a physics and math major in college, and I was quite fortunate to have a good undergraduate research experience, which really sort of got me into the mode of doing research and what's exciting about doing things that other people haven't done before.
Mm-hmm.
And that really got me launched.
That's very interesting. You found out that you like physics at the age of 7 or 10.
Well, I think when I was 7 or 10, I was still I didn't know what physics was at that age. I liked science in general. I liked playing with. In my generation, there were kids who liked to tear apart, radios and put together circuits again,
Mm-hmm.
and play with that kind of stuff, which I did. But so I like science and I like mathematics, but I didn't really even know what physics was until I took my first physics course, and that was in high school.
Right.
So
how did you end up doing topological quantum computing?
yeah, that's actually a bit of a long story. My undergraduate research project was actually in physical chemistry. It's close to physics. I sort of view it as being a physics project. And then I went to graduate school. I didn't know what I wanted to do. I did think about high energy physics. I thought about doing, GR type cosmology things. I thought about doing things that were very mathematical. Things that I these days I kind of don't have a whole lot of patience for. Things where people do really delta epsilon proofs. And by doing delta epsilon proofs of convergence of field theories and things like that, people do learn things, but it's very tedious, and it takes a particular type of personality that's definitely not me, to be able to do that work and do it well. And so I explored that, and eventually I sort of came to condensed matter, which maybe it was what I should have started with, but at least I'm glad I sort of looked at these other fields as well. And in condensed matter, it was a little bit random. I was at Harvard, and there were a number of supervisors. who were all very good. And I was sort of assigned randomly a little bit because there were too many students who wanted to do condensed matter, and there was a little bit of I wouldn't say a lottery, that they sort of had us all give presentations and then sort of divided us up. And I ended up really fortunately with Bert Helmer as an advisor. And at the time he was really, and for much of his later career, he spent thinking a lot about quantum Hall physics. And at that time, they had just made a really important advance in understanding certain types of quantum Hall states using what they now call composite fermions or Chern-Simons fermions. And so that was a lot of my dissertation, and I got really involved in that particular field. But on the side, at the same time, I spent some time just reading other things to find out what other things were going on. And I just happened to go into a bookstore and picked up a book, which I must have gotten for cheap because it's actually a really expensive book. It was probably a used bookstore or something. I picked up this book by Louis Kaufman called Knots in Physics. Mm-hmm. And I started reading this, and I was just, oh, this is so beautiful. This is so beautiful. I have to do something like this. And I spent some time, I didn't know how it was going to be applied to what I was working on. And I spent some time trying to think about some other physical systems where knots might be important. Polymers and actually vortex lines and superconductors, they can knot around each other and so forth. And I kind of felt like the really super powerful techniques from those books weren't so applicable to the physics in those systems. I mean, you can say something about it, but it doesn't go that far. And so I sort of just forgot about it for a little bit. But then a few years later, people started thinking seriously about non-abelian anions. And that I recognized immediately, that's what it is. That's exactly what they're talking about. And I was like, okay, that's what I'm getting involved in. And it was, by that time I had moved to Bell Labs, which was really the world home of quantum Hall physics at the time. And it was a really good opportunity for me to get involved in this field that I thought was really exciting and really beautiful. And the field was booming at the time with a lot of investment from Microsoft in particular, trying to push the idea of topological quantum computation using some of these quantum Hall systems as a platform. And it was probably 7 more years before they decided that quantum Hall maybe wasn't such a good platform to really invest their energy in. But 7 years was plenty of long time for me to get really deeply into that field and really learn an awful lot about it and how it's related to physics and what the exciting things going on are in that direction, and how they relate to condensed matter physics on the one hand and mathematics and topology on the other hand. And that's kind of the path I guess I took. Mm-hmm. and so here we are.
Right.
Yeah.
Could you talk a little about what really is topological quantum computing?
Yeah, good question. So it actually it's become in its simplest form, the idea is that you have these particles that we call anyons, and special anyons, non-abelian anyons, and they live in usually a two-dimensional plane, and you imagine that you can pick up the particles and move them around each other, and this procedure is in principle enough to be able to build a quantum computer. If you have the right kind of particles living in your plane, all you have to do is be able to move them around each other and then measure them, and you have a quantum computer. And that sounds extremely appealing because it seems like a really simple way to make a quantum computer. It also has some theoretical advantages, which is that quantum computers are exquisitely sensitive to noise in the environment, and this one isn't sensitive to really almost anything in the environment, as long as you can know accurately what path the particles took topologically, that this particle went around that one. You don't have to know the detailed path if it went in a wiggly line or went in a straight line. You just have to know that it went in a line, somehow in a path going around the other to form a particular knot. And that also is appealing, that you have a robust way of doing quantum computers that doesn't depend on details and it's really immune to noise. So it sounds like a great idea. But it turns out to be harder than imagined for many reasons. And Microsoft is still pushing the idea of topological quantum computing very much, and they just had some big, possibly overblown press releases on talking about the advances they've made, and the advances are really interesting advances from a condensed matter and standpoint, and even possibly from a quantum computing standpoint. But the computer that they're pushing now, it has some of the same ideas, but it's gone quite a distance from that original vision, and it has some, from a technical standpoint, it has some potential liabilities besides being a long way behind some of the other approaches to quantum computing that people are pursuing. It has some technical liabilities which may make it not such a promising path after all. I mean, it's sort of in the list of sort of techniques that people are still pursuing, which are somewhat behind the leading techniques, but have some possible advantages to them. But if you were an investor or a venture capitalist and you were trying to invest in one quantum computing company, I'm not sure I would choose Microsoft as my first. This is not advice for investment. I'm not an investment manager, but I'm not sure I would choose Microsoft as being particularly more promising than some of the other approaches, which all have their advantages too. But I mean, it's certainly, I'm very happy that they've been pushing this direction, because a lot of very good and very hard science has been done, and a lot of money has been invested in pursuing this avenue, and it's always good to push scientific achievement in that direction, because knowing how to do these things is something that even if it's not useful for doing what you're trying to do, it may be very useful for doing something else. It may be that in the end, this advantage does have enough. This approach does have enough advantages such that it becomes a real competitor to the other approaches. Right now, it's to be honest, it's quite far behind.
So topology is one of the ways to build a quantum computer.
Yes. Yes.
And there are other ways.
There are many. Well, actually, glad you asked. So they have these topological qubits. There are many ways to build qubits. There's superconducting qubits, ion trap qubits, there are optical. I mean, there's all sorts of types of qubits that people are working with, and each of these make a platform for do you build? It's like asking, do you build your computer out of vacuum tubes, or do you build them out of silicon transistors? Well, okay, in the end, we know that silicon transistors are better, but you could build them out of vacuum tubes, and once upon a time they did. And then silicon came along, and people are like, oh yeah, this is really a lot better, and so you can build much bigger computers. So this is the state we're in now, but we don't know which one's the vacuum tube and which one's the silicon. So we're still trying to figure that out. But some of the qubits are microscopically topological. But once you have a big set of qubits, there's always going to be some amount of error correction that you need to do on the qubits. And so people start asking about, well, what kind of error correcting code can you build? And many of the best error correcting codes are based on the toric code or the surface code, which is basically another topological system. So you take your microscopic qubit, which may not be topological, and then you build from it a topological system. So topology comes back in another aspect as well, and is interesting in its own right. Even if the computer that you build in the end doesn't work with microscopic, topological qubits built from quantum Hall states or or myron or fermions or something. It could be built from ions, or it could be built from superconducting qubits, or all optical. But then once you start trying to put error correction in, many of the strategies, and possibly what currently looks like the best strategy, is to build a topological state out of them and then use that as your error protected qubit. So topology comes back in another aspect.
Right. So coming back to your lectures, which I did on topological quantum, one of the interesting things that I also loved listening to were the little history snippets in between the lectures, and also in your textbook.
Yeah. So I like doing those. I mean, part of it is that I enjoy finding out these little bits of history myself. And life is a story, and you want to hear it. Everyone wants to hear stories about how did this come about. And and sometimes, I remember when I learned about quantum mechanics, and a lot of quantum mechanics courses start with the history of why did we need to throw away classical physics. I actually didn't have a lot of patience for that, actually. I felt like, I'm here to learn quantum mechanics. Just tell me what is the truth, and I sympathize with that. But on the other hand, understanding some of the people involved and what they were doing, what they were thinking, is sometimes actually really, well, it's really interesting and really productive in other ways. And you learn a lot about the details of what goes on. I mean, you can learn, the various stories about, Camerleonis and the discovery of superconductivity and superfluidity. And, you can read textbooks on superfluidity and never actually, unless you're doing the experiment yourself, never actually notice how dramatic it actually is when something goes through a superfluid transition. That you have your cryostat, and the cryostat is literally shaking because of all the boiling, and then all of a sudden you go through the superfluid transition and it's absolutely quiet. And that's actually not in most books on superfluidity. They leave that to the experimentalists. But to really understand that this was a really dramatic effect that he took, even though I'm sure his lab was probably, all full of noises and shaking and everything, is because these are all primitive pumps and primitive everything. But still, it would be something that he noticed, and he did notice, and he wrote down in his notebook, and he said something's happening, and we're going to go back and eventually figure out what that is. And they eventually did, and figured out this was a superfluid transition. To learn it, hearing that story is something that if you didn't hear that story, you wouldn't know how dramatic this physical effect actually is, unless you've actually done the experiment yourself. So it is useful to have a little bit of understanding of where these things come from. And in some cases, it's interesting to highlight some of the characters in the history who are unusual for one way or another, who maybe come from different backgrounds, or and were able to achieve great things, or maybe were stopped from achieving great things for one reason or another. I was just visiting Nottingham 2 weeks ago or 3 weeks ago, and they're very proud of George Green, Green's functions, Green's theorems, mathematician who lived around early 1800s, and he had 1 year of formal education. He worked in a mill. His family ran a mill, and they owned some properties, and he lived by renting the properties and milling flour. And he had 1 year of formal education when he was like 9 years old, and that was it. And it's like Ramanujan, he just figured out all this mathematics by himself in his spare time. And he, derived all these theorems, and he learned all sorts of things about differential equations and so forth. And he sent some of it off to Cambridge to have them look at it, and they felt like they just had to get this guy to Cambridge. And apparently they said, I was told that they sent him a letter, please come to join us at Cambridge for a year or two. And he didn't even think the letter was real, because he couldn't imagine that people would be interested in this kind of thing. So he ignored it. And it was only after like another year or two, where one of his friends had run into one of the faculty from Cambridge. I mean, people didn't travel around that much, as much as we do these days. So that's a sort of an unusual occurrence back then. And the person from Cambridge said, "Oh, you have to go talk to your friend and tell him he has to come to Cambridge." So he went to Cambridge for like 1 or 2 years or something, very short time to get his degree, and they invited him to be faculty. But he said, "No, I have to go take care of the mill. It's really important." So he goes back and takes care of the mill, and I think he just dies a couple of years later. And he wasn't that young. He was already, in his 50s or something. He was not that young by the time he had gotten there, but he had invented all this mathematics, which is incredibly important, and it was way beyond anything that the people at Cambridge were doing, and it's incredibly important. We still use it today, and Green's functions are everything, and he was just he was just doing this in his spare time. Mm-hmm. He was just interested in, and that wasn't his day job, so he really. Unusual and maybe not as extreme as Ramanujan, who people still have no idea how he comes up with these things. I mean, it's just absolutely out of the blue. These crazy mathematical results that are apparently right, and no one has any idea how they came to his head. And sometimes he would say, "Oh, I saw this one in a dream" or something. But it just seems like it's from outer space or something. I mean, these people are just incredible. They're from a different planet. Yeah, kind of interesting. So.
That is very interesting. I remember you talking about Jim Simons. He developed a very fundamental theory, which is Chern-Simons theory for topological quantum.
Yes, absolutely. And actually, he was a fantastic mathematician in many ways. And if you talk to certain mathematicians, they actually know him not even for this work. They know him for other work he did. And I think that he worked in the idea of minimal surfaces. Like if you have a one-dimensional wire and you make a soap bubble out of it, you put it in soap and you bring it up and it's going to be a bubble. It will form the smallest two-dimensional surface that's bounded by the one-dimensional object. So like if you have two rings, it won't form a cylinder between the rings. It will form sort of like a tube that gets smaller in the middle and wider on the sides, because that's actually less area. He apparently has some beautiful theorems on minimal surfaces, and they don't, but what we remember him for is Chern-Simons theory, which was done long before most physicists were thinking about it. I mean, I guess there were a few who were sort of in that space a little bit. But most of the work in Chern-Simons theory got interested in the late 70s and early 80s. And then the end of the story, for those who don't know, is he left mathematics to start a hedge fund, which became one of the most successful hedge funds in the world, and his net wealth went up to tens of billions of dollars, and he passed away just last year, I think, and he left a lot of his money to funding science. So he funds mathematics and physics and I think neuroscience also. He's interested in neuroscience as well. I mean, he's been a huge funder of the scientific endeavor, which is great. This really interesting person. It was sort of interesting that there's the Simons Center. He was a faculty at Stony Brook, and that's where his hedge fund was on Long Island. And he built this huge building at Stony Brook, the Simons Center, which I think he built other buildings as well, but there was one at Stony Brook, beautiful building for holding mathematics conferences, an excellent cafeteria too. And he used to come to the conferences, and he would sit in the front row and listen. And apparently it was not that unusual during mathematics talks or physics talks that someone would ask a question, there would be silence, and he would say, "Oh, actually, I know the answer to that." And he would actually answer some of the questions. And other people, this is professional conferences, people who are at the forefront of science, and he really just knew enough about it that he could occasionally give the authoritative answer on certain topics that other people didn't know. Mm-hmm. So he was really a rather marvelous person. Very, very impressive in many ways.
Right.
Yeah. I mean, there are a lot of really impressive people in the fields of physics and mathematics, people who are really mind-bogglingly smart, and it's generally a bad idea to compare yourself to them because you're always going to find some person who's just out of the world amazing, and it's hard to sometimes it's really easy to have an inferiority complex, or what they call them, imposter syndrome. Feel like I'm not suited for this field, because you have people like Alexei Kitaev and Jim Simons and these people out there who are just miles ahead of everyone else and think so much deeper. But I like to think of it kind of differently, that these are the high priests of the field, and they need monks in the field who appreciate what they've done and can work with it. That the high priests make the enormous advances, and then the monks fill in a lot of the details. And even being able to rise to the level where you can understand what they're talking about and be able to, quote, fill in the details or apply it to certain experiments or something like that is very hard, and is an honor to be able to be in that select circle of people who are able to do those kind of tasks, even if we're not the ones who make the absolutely enormous breakthroughs. Well, okay, I once had this discussion with someone who was in school with Eva Silverstein, who's I think she's at Stanford, faculty in string theory, and I think was obviously very highly regarded, and one of the best in the field. And she said, "Well, the thing is, you can always feel like other people are the leaders, and you're not the leader." She is one of the leaders, but the thing is, it's like a bike race, that there's there's the one person in front, and they're doing a lot of work in the bike race, and there's the whole peloton, this crowd of people who are all behind them and they're doing less work, because they have the the person in front has to get all the air resistance, and the peloton saves a lot of energy by not having to ride in front, and they're able to keep up with the leaders because they're not doing the hardest work. But then occasionally someone from the peloton will sprint up ahead, and they'll be the leader for a little while, and you never know when that's going to be you. You might do something which turns out to be important, and you'll be the one sprinting up ahead and doing the hard work, and everyone else falls in behind you, and then maybe you'll fall back into the peloton. So it's even the people who are just the monks and not the high priests sometimes make occasional important advances, and everyone follows.
Right. Yeah. That's a very interesting metaphor.
Yeah. Yeah, I think, I can't remember if that was, if she came up with it or if I came up with it. I think maybe I came up with it, but then she said, "Yeah, but you can sprint up ahead," or something. Anyway, it was a while ago.
Okay. Professor, do you have a favorite physicist?
Oh, wow. There are a lot who I really admire. In some ways, there's always this is a good question. A lot of times, it's not a great idea to have heroes sometimes, because sometimes the heroes have things in their closet. Like a lot of people would say, "Well, Richard Feynman, he was so amazing," but actually, if you read his biography, he was not a nice guy in a lot of ways. I mean, a lot of people loved him and thought he was so charismatic and charming and so forth, but he had a lot of skeletons in his closet which were not nice, and okay. You can start psychologizing him and trying to understand why he had bad behavior, but kind of doesn't excuse the bad behavior. I mean, he had some horrible experiences in his life also, which he didn't deserve, but doesn't give him the right to be a bit of a jerk. So it's, I don't want to sort of stick my neck out and say, this is the person who I really, but Marie Curie was one of the people who I always thought was extremely, extremely impressive, and so brilliant and so devoted. So, yeah, and I think everyone has. I mean, I don't think anyone's going to come up with new skeletons in her closet that we haven't heard of. So I know her biography. I mean, there was. When she was alive, there was some times when she was not popular, there were certain scandals and so forth. In retrospect, we like, yeah, whatever, but just her, obviously a genius, and an extremely hardworking genius. Amazing. Yeah.
Do you have a favorite particle?
Oh yeah, well, it has to be the anion. I'm not sure which anion I would choose. The Fibonacci anion is an old favorite, I guess. I've written a lot of papers on the Fibonacci anion. Everyone likes Majorana Ising anions too. I'm not sure. I think that other people have sort of done a lot of work on Ising anions, so maybe I'm not gonna say that's really a favorite. Maybe the Fibonacci anion. It's a pretty simple one, and it's a good one. It has a lot of good physics wrapped up in it. Now I'm going through various topological quantum field theories in my head to see if there are others that are really nice. Yeah, let's stick with the Fibonacci anion.
What kind of personality does a Fibonacci anion have?
What kind of personality does it have? Oh, they're friendly sorts, I don't know. I don't know. That's a good question. I mean, in most of my slides, the Fibonacci anions are red.
Okay.
I think. I'm a little bit colorblind, so I actually don't remember, but I think they're red. Yeah, I'm not sure. It makes them fiery or something. I don't know.
All right.
Yeah.
Thank you so much.
My pleasure.
Lovely having this conversation with you.
It was really fun.